Okay guys, so we are here to look into how differentiation will work numerically in programming. So we have been taught of how derivatives are done analytically, classically. So we have memorized a lot of formula, but now we will be doing it in the context of putting the algorithm into the computer so we can use it as we will be needing it in any structural analysis procedures. Okay, so the derivative of function f of x at a certain point, let's say x equals a, is defined in elementary calculus as the limit. Okay, so the limit of the ratio of delta y over delta x as delta x approaches 0. So that is actually the exact definition you can find in most elementary books in calculus. So there's a slight a change here on the definition, because instead of considering the increment delta x as our point of reference, we consider the interpolating value of the function uh, over the range x exactly at point A. Okay, so if you will notice, this is basically delta x approaches was changed into an x approaches A, but they are not different. Okay, so if I have here a graph of a function, let's say I have a graph of a function there, and I want to take the limit, no, upon which say the derivative at a certain point A is, okay, so I want to look into this uh, exact point as my interpolating value of x. Then I will consider now maybe a positive delta x or a negative delta x somewhere here. Okay, so if I assume that this is now my my other point defined by this increment, let's say delta x. As delta x approaches 0, your x value at that point becomes a. Okay, so x at that point will approach the value of a as delta x approaches 0. So we didn't change anything about the definition, only we changed the form so as to match our procedure later, but it is still the same derivative we have defined during our college days. Okay, so to proceed with my discussion here on differentiation, so if I have now a a function, say okay, so if I have now a function, okay, upon which an interpolating value again, say a is being evaluated. Okay, so this is x equals a, and I would like to compute the ratio or compute the limit of the ratio. This is actually a delta y. Okay, if this is y, I have a functional value here exactly at f a. Okay, so this the measurement of such value, height, okay, that is touching the curve at x equals a is actually f sub a, and maybe another value here of f can be computed at a certain increment, let's say delta x, having of course a value equivalent to f of a plus delta x. Okay, so I'm just trying to get, okay, on the numerator the difference delta y, okay, because this is your first functional value of y, and this is the second functional value. If I subtract the second or the first from the second, I get my delta y there. So the limit of this ratio as delta x becomes smaller and smaller until it approaches 0, and x is defined exactly at that point a. You have no choice but to interpolate it at that point. Then you are actually simply looking at the slope, no, of a line that is connecting these 2 points here. Okay, so you have now this slope. Okay, that's why derivatives are defined sometimes as the slope, the gradient, the rate of change, etc. Okay, you can say that this is the rate of change upon which your delta y is uh, proceeding as far as this delta x is concerned. So this is the rate of change of delta y with respect to delta x. So derivatives can be regarded as slope, can also be regarded as rate of change. And exactly at the point in which this limit is achieved, then we can say that your derivative now becomes, okay, a tangent line that is actually touching or passing the curve at only one point within the vicinity, uh, uh, within this vicinity. Hence, the only difference between a derivative and a slope is when your delta x is not yet has not yet achieved its final limit as to approaching 0. Okay, so approaching 0 means it becomes very very near but not equal to 0, or else this limit here will actually be misbehaving uh, when you have a denominator equivalent to 0. So what we did actually, class, here, the interpretation of what I did is what you call a forward difference approximation as far as numerical differentiation is concerned. Okay, forward means you assume a value of delta x past the value of your first functional value f of a. Okay, and if we try solving this function here using the concept that I just gave you, okay, so we can make use of approximations wherein I change my increment uh, initially set to 0.05. So I set my increment initially, so this is the initial value, and then I made use of a divisor that uh, that will reduce the increment into half its uh, uh, half its previous value. Okay, so what we are doing is we're trying to set the delta x increment approaching 0 but not exactly 0. Okay, so my increment divisor now, to make this 1/2 of the preceding value, is 1, 2, 4, 8, 16, etc. Okay, and my forward point, a plus delta x, which is the value of x here, this point. So x here is actually a plus delta x, becomes this one here. And if I do the limit formula without considering the classical definition of a derivative of the function, because computers cannot understand what is the derivative of an exponential function, etc. It will do only simple procedures, but very efficiently if you do the program correctly. So what the computer will just do is to evaluate, okay, FA. What is this again? This is the delta y and the delta x, okay, until such time wherein the error becomes very small. So how do you know the error? The error can be computed numerically also, or you can also compute the error by comparing it with the exact value. Okay, so error analysis is a different has a different a program of discussion. So mahirap ipasok yung error analysis ngayon, and those are only for more importantly used by mathematics major. So we will get rid of it for now. We'll avoid doing some error computations for now. Okay, so what is important here is you know the procedure for you to be able to program it later in case you need them. Okay, so which is the correct value here? Of course, you have to compare it with the exact value you can get from the analytical solution. Okay, so you differentiate the function and it will give you this value. So this is the exact value, if you will, do it analytically. Of course, you have to know the derivative of a product of two functions, which is an exponential and a trigonometric function there. Okay, and how to get the error is, or the discrepancy is, just to subtract whatever you get from here. You subtract the exact value and you get the error. Unfortunately, class, if you will look at the result of Whitley, it will be a different set of values that you can see. Okay, because of the round off error and because of truncation errors. Okay, so round off errors are errors due to cutting off some decimal, rounding off some decimal values, and truncation errors are just the same, but they are more uh, focus on the succeeding expressions. Let's say you have a polynomial, interpolating polynomial in the third degree, and then you truncate it only in the second degree, or you're using a power series, a Taylor series, a Maclaurin series. Whatever you truncate on the expression will give you an error, a larger error, or maybe, yes, a larger error than truncating it, not truncating it. And rounding off is just the same. So only the difference is in rounding off you are dealing with the numbers already. No? Okay, so that's the difference between the two. Okay, so you might be wondering bakit hindi pareho, kasi iba yung ginamit kong decimal places here, and yung pag-compute dun sa libro is also different, kaya iba yung point of comparison nila, no? Okay, but the exact answer is very close to it. Okay, so this is actually using 12 values of your increment delta x. Okay, so for the backward difference technique, the procedure is similar. No? Of course, they are not the same, but it's similar. If you have here the y-axis and you have here the x-axis, and you have here the graph of the function. So what you do is you set an interpolating value here. Let's say x equals a, and then instead of having a forward increment, you just get a backward increment. Let's say here, so what's the value of x now here? So x becomes a minus delta x. Okay, so that point is x is equal to a minus delta x. Okay, so our formula now will be a little bit different. Nauuna yung FA, mauhuli yung F's of a minus delta x there. And if we try solving it just the same, I will be looking into another set of derivatives. Okay, so these are limit derivatives. And they are not totally different, because if you are going to look at this point, it will still converge here at this point. The only difference is if this curvature here is not the same curvature there, but the backward and forward difference for very regular functions does not actually uh, give you very different results. Okay, which is the closest? They are just the same. 1653. Here you will take note that this is 1654. So you can still extend it down to get 53 maybe here, while in the forward difference, I think we have captured 653 here. No? So if you are to compare the two, slightly your forward difference converge faster than your backward difference technique. Okay? Okay. Okay, so these are the results as I have told you. Now, the truncation and the rounding off error gave the computation of Gerald Whitley in the book to converge into the exact value at the eighth, okay, at the eighth increment. Okay, so maganda yung pag round off niya. Kahit na marami yung decimal ko, mas mabilis pa rin siyang nag-converge sa kanya. No? So again, it depends on how you round it off and how you truncate your expressions, no? Your series expressions. And the third technique using this approach is called the central difference technique, which is simply putting the interpolating function, okay, in between. Okay, so let's make use of curve that's not symmetrical. Okay, so dito siya sa gitna. So this is A, x equals A. So what the central difference technique did is to use the forward and the backward difference, okay, and make use of this as your approximation. Okay, as delta x, both delta x approaches 0, of course it will converge here at the middle, and therefore your slope will here, your derivative here will actually be represented by this initially. Okay, so this is now x plus delta x, or a, sorry, it's a plus delta x, and this is a minus delta x. Okay, so you have here now the function, and of course, since this is centrally placed, your increment will double. So this is 2 delta x. Okay, and if we try solving this, we will have this forward point, this is the backward point, and this is now your limit derivative. Okay, so for this is 1653 actually converges somewhere on the 2, 4, 6, 7, no? Seventh increment. So to compare the central difference with the two techniques, of course, we can generalize as far as this example is concerned that the convergence is much faster, no? Uh, because you have explored both sides of the region where your interpolating value of x is located. Okay, so this is now the results of Whitley. On the Whitley's approach, dun sa fifth, nakuha na niya, no? Yung convergence niya. So still, it's a matter of how you do the rounding and the truncation of your uh, a series of approximation. Okay, so that's the first topic I'd like to present now. Of course, this is not the best way to deal with numerical differentiation yet. So we will move forward to the divided difference technique on the next video. Okay.